then I would simply have these arrivals like this. Maybe the reflection's a negative polarity. This is time along this axis, and this is the particular geophone right there. All right? So the geophone is measuring, without the distortion of the geophone, it's measuring essentially the impulse response of the system. So I think about this process as a linear system. All right? So I have an input, and then this whole thing here, I'm going to call the response of the Earth. Okay. It's whatever the Earth is going to respond. And if I think about it as a linear system, if the Earth responds linearly to the signal, then I can just convolve these two. And then I'm going to convolve that with the geophone. And I'm going to call this S of t, because that's what we've always been calling it. And this is geophone. And this is the output of t. Okay. So, what do I have in the frequency domain? So in the frequency domain, I'm going to have the input, I'm going to have the Earth response and a multiplication, and I'm going to have the geophone response. And actually, we talked about this as a source signal, I'm sorry. Yeah. Well, good question. So if I put an input into G of t that's just a perfect impulse, I'll actually get a little waveform. So the geophone actually has a response to an impulse that's not perfect, and then you get the output after that. Okay? So you could think of it, I guess you could think of this as just a response function of the phone. If I hit it really hard, it's going to vibrate a little bit, even with a perfect. Yeah, exactly. I'll leave it as that. That's a really good question. Okay, so this is how we represent the output. Now, this thing is simply a sequence of impulses, right? We've called the Earth distortionless for the time being. So it's not going to change the spectrum or the frequency response of the signal at all. The source signal is whatever it is. For the most part, what we see in the frequency domain is, if we had a hammer blow, it might look something like this. Okay, this frequency might be 10 hertz, and this frequency might be 300 hertz. Okay, so this would be the source frequency. This is amperes. That's S of S. The Earth response, we're going to basically right now, if we assume that everything's a ray, we're going to call the Earth response simply this. That's E of F, right? When we think about one arrival, it's an impulse. It'll get a little more complicated when we talk about it later, but let's just assume that for the time being. And if you remember some of the pictures that were in the notes last time, the geophone is a damped spring. Remember that? It's actually a spring sitting in a mass, and it's basically in an overdamped situation, right? And so it has a response depending on the frequency that we saw that looked like this, and then it drops something like that. So this could be, for example, a 10 hertz geophone. And then this thing happens is that the geophone is got a fairly flat response from about half of the, or it can be used anyway, between about half of the resonant frequency all the way up to about 20 times the resonant frequency. So all we have to do to get the output spectrum or the output frequency response is multiply these three things together. We multiply these three things together and we get the output. Okay. Now, this is where filtering comes in. All right? Let's say that my source signal, or let's say that the earth response isn't perfectly flat, that there's some kind of tuning of the earth response. And let's say that the earth response looks something like this, just for grin. Let's say it's this, and then there's another one up here. And this thing represents surface waves. And this one represents, say, head waves. And they're at different frequencies. The surface wave is maybe about 15 hertz center frequency, and the head wave is more like up at 60 hertz. Yeah. So the Earth itself actually doesn't behave perfectly as a ray. It actually separates the arrivals into different frequency ranges by some mechanism that I haven't explained yet. So if I want to take this signal right here, so I've got the surface waves, and then I've got the body waves. So this is frequency, and this is E of F. Suppose I want to isolate the surface waves. How would I do that? Well, I might simply block off a range of frequencies and basically just window, take only this area right in here. So essentially I'm multiplying E of F by some window function. And after I do that, I'll basically just get something like this. I'll only isolate this zone and I'll make the rest of this stuff 0. And I could do the same with the body wave arrival. This process right here, and most of you know what this thing is probably, is known as a band pass filter. All it is multiplying your signal, your spectrum, by an appropriate window function. Certain width, certain center. How would I isolate one frequency? Like maybe I want to isolate just a small range of frequencies. Well, I can do the same thing. I can basically multiply by a very, very tight window function. And I can pick out an individual frequency. So imagine if I did this for one of the surface waves. If I pick out an individual frequency, I could measure the slope of that frequency, which would give me the velocity of that frequency, which would give me a point on the dispersion curve of the ground roll, and I could do that at different points. So this is a way of isolating certain frequencies, and it's a way of improving the data quality for an arrival that you're interested in. And it's probably the most Yeah.
team just, I mean, he's a hot quarterback. It's hot. And the keeper, I think Packers should do more of that. Short passes, long throws. Like when they got close to the end zone, instead of going for the end zone each time, they should have gone short passes. The guy gets tackled, the clock's moving.
And they never throw Packers don't throw screens.
Yeah. They should be throwing